Okay. The mean value theorem for integrals states that somewhere between the inscribed and circumscribed rectangles, there is a rectangle whose area is the same as the area of the region underneath the curve. So let's look at a picture to kind of clarify this a little bit more. So the idea is, let's say we're looking at a function and we're trying to find the area underneath the curve from A to B. So let's say we're trying to figure out what that area is. Okay, let's draw a couple different rectangles. So let's say same function, here's A, here's B. Let's just go ahead and draw one inscribed rectangle. So this would be an inscribed rectangle, this would be considered a right hand, and obviously the area of the rectangle is less than the exact area of the curve because we're missing this little piece right here. Okay, if we do the same thing and draw, let's do a circumscribed, or let's do a left-hand rectangle. So that would be the area of the rectangle, and notice this is an overestimate of the exact area because obviously we've got that extra piece there. So what the mean value theorem says is if you actually have a continuous function from A to B and you want to try to find the exact area underneath the curve, somewhere on this curve you can draw a rectangle that would actually give you the same area under that curve. So there's one rectangle you can draw that gives you the exact area underneath the curve. And wherever it hits that point on that curve is going to be called C. So this is what this is saying. If you have a continuous function, this is the exact area underneath the curve. That would be this, right? Area underneath the curve from A to B. There is a place where the area of the rectangle, so if this is the rectangle that we came up with, the width of the rectangle is B minus A, and then notice the height of the rectangle is whatever the y value on the function is at C, which is f of C. So this is just saying there is a place where the area of the rectangle, this is the rectangle, one rectangle that we drew, is going to give you the same area as the area underneath the curve. Now, typically, we're not going to actually see this written this way. Notice I can go ahead and solve for f of C by dividing the b minus a over. This is the form that you're going to see most of the time, and this is called your mean value theorem for definite integrals, or if you think about the word mean, it's another word for average, so we also call this the average value. Okay, so geometrically this is just the same thing that we drew up here. Okay, so let's take a look at one function. This is the graph of 6 minus x squared. And I want to find the average value of this function from 1 to 3. So if I ask you to find the average value, I am looking for the y value. So I'm actually trying to find f of c, which is 1 over b minus a, times the integral of f of x dx. So this is really your average value. And if you think about what we do for an average, we add up a whole bunch of stuff, divide by how many terms you have, and that's really what's happening here. What you're doing here is you are adding up all the y values, you're summing up a whole bunch of stuff, and this is where you're dividing by that interval. So that's why it's called your average value. So let's see what we have here. So this one, we do have an equation. So this is your A, this is your B. So it'd be 1 over 3 minus 1 from 1 to 3 of 6 minus x squared dx. So this is 1/2. And I can take the antiderivative, just 6x minus x cubed over 3. And my bounds are 1 to 3. I'm going to pull this 1/2 in the front. And if I plug in the 3, I have 18 here. This is going to give me 27 divided by 3, which is 9. And now subtract off what I get when I plug in the 1. So this is 6 minus 1/3. So this is my average value. Clean this up a little bit. I have 9 minus, this is really 17/3. So 1/2 times 10/3, which really gives me 5/3. So this is the average value of this function. Another way to think about it graphically is, so this is f of c, which is a y value. So 5/3 is like 1.6, so it's somewhere around here, right? So this is saying, another way to think about it is we were only looking at this graph from 1 to 3. So if you look at this graph from 1 to 3, this is saying the average y value on this interval, if you add up all the y values and divide by that interval from 1 to 3, is going all the way to here actually, is that. And that makes some reasonable sense. If you add up all the y values, there's a bunch of positive, there's a bunch of negatives. So the average y value is 1.6 something.